Now I'll just jump into the presentation of the dynamic simulation here. So first, in today's presentation, first we will start with a short introduction, and then we will go through a simple circuit presentation and the analysis and the advantages of using the dynamic simulation. Then later we will see the new options that we have added to the simulator, as well as to take advantage of these new options, we have improved few component models as well, both in hydraulic as well as in electrical part. So we will see both hydraulic and electrical components together as well. So first, in Automation Studio, a dynamic simulation represents a dynamic component behavior and the adjustable simulation pace here. With the new option now, it is possible to adjust the simulation pace. When I say adjusting the simulation pace, it means that the number of iteration time. So as you can see here, we have added 3 options to the new simulator. The first one is the normal simulation, which is basically our previous version, which is 10 milliseconds. And the new options are fast simulation, which iteration is carried out every 500 microseconds, and the advanced simulation, which is carried out 100 microseconds. Basically, it means 0.1 milliseconds for advanced simulation and 0.5 milliseconds for the fast simulation. And to take advantage of this advanced simulation behavior, so we have improved few component models as well. Like as you can see here, a hydraulics proportional valve, a dynamic model is added, and also improved a fluid power cylinder and electrotechnical motor as well. Now let's move to the Automation Studio software to show you how to change the simulation pace and what effect it has in the simulation, as well as we will see the improved component behavior. So first I would like to start with a simple example of electrohydraulic application. I'll just open first a simple electrohydraulic pump application here to show you the difference between the normal simulation and the fast and the advanced simulation pace. First, to explain the circuit here, what basically I'm doing here is, at this point in this one here, if you look at it, there is a simple, in the hydraulic side there is a pump, which is controlled by the PID controller in the electrical side, and we have a motor which is can be applied with the resistive torque using this pedal over here. And using the set point devices here, we are controlling the differential pressure between this pressure gauge and this pressure gauge. By controlling the pressure gauge, it automatically gets the feedback from this controller to monitor the flow. And if you look at the plotter here, the yellow color one is the flow, and the green color one is the differential pressure plotter here. So now I will start the simple normal simulation here. So when I do a normal simulation, so automatically you can see here in this graph, there is a small steps created in this plotter. So when it slowly starts going, you can see here the response time is a bit slow with the normal simulation. So you don't have a stable flow going through this line to control this motor. So how do I know it's a normal simulation? You can just look at here as well. There is a simulation pace and there's a normal simulation. So now we will see the new advanced option, how it affects the simulation behavior here. So for that, I will just stop it. And I'm going to access the project properties. And under the standards, if you just see here, there are 2 tabs, addition and the simulation. If I go to the simulation tab, you can adjust your simulation pace here at this point. So if I just open, there's the 3 types: a normal simulation, which is 10 milliseconds, and fast simulation, and it's a 0.5 milliseconds. And if I go to the advanced simulation mode, it's a 0.1 millisecond simulation. Now let's see what effect it has to the fast simulation over here. So I will apply to this project right now, and I will close it. So I'll just run the simulation again, normal simulation here. Now you can see here the curve is a bit more smoother than before with the normal simulation. And as the simulation goes on, you can see here you get the steady flow out of this pump to control this motor over here with the fast simulation, 0.5 millisecond simulation here. So now let's see, like, if we wanted to have an advanced simulation, what effect it has. So I'll just stop this one. I'll once again go back to the project properties, projects and standards, and I go to the simulation and then change it to advanced. So I apply to this project right now. I see this here. So if I run the simulation here, you can take a look at here. The simulation phase is advanced for this project, and it's even more smoother curves because the number of iteration time is really very less, which is like every 0.1 milliseconds here. So now you can see here it's more smoother curves that you get, the flow that you have. So if I adjust my differential pressure at this point using the set point devices over here, by adjusting this, you can see here the flow automatically adjusts to itself. So now if we wanted to see the effect of the external load acting on this motor, how the pump behaves, if I just click on this pedal over here and I apply some resistive torque to this motor to see the effect of flow in our plotter. So as you can see here, it's more like a real-life application, like a real-life example. So there is some small fluctuations here, which is basically due to the external load acting on the motor. So this is how you can take advantage of this new simulator in the electrohydraulic applications. Now I just wanted to move on to the electrical application as well to show you like what effect it has on the electrical side as well to begin with. And later we will go through the new improved component models at that stage as well. So I'll close this project for now. And I'm going to open one of the electrotechnical projects. So this one is actually like we have created a simple filter. So it just takes a bit more time here. So okay, so now if you see here in this one, there is a simple linear system that we have, a simple linear electrical filter system that we have created here. And we have a simple input that we are giving, and what we are going to see the output of this electrical system over here. What we are going to do in this project is that we are going to give a simple sine wave input to this one, and after the filtration with the resistance, inductance, and the capacitance, we are going to see the output here, and we will monitor using this plotter over here, and by adjusting this frequency over here. So now I will start the simulation right now. Under the simulation, normal simulation here. Right now you can see here both input, which is green color, and the output is of the same phase, and there is not much difference between the amplitude, as well as there is not much difference in the phase lag as well. So for example, if I'm going to adjust my frequencies here, you can automatically see here when it goes, there is a simple phase lag appearing at 37.9 Hertz. So if I just keep on increasing, the output and the input has a phase lag of 150 degrees, and the amplitude is also changes. When I further increase it more, there is a cutoff frequency by the filter. So you can see here the output signal has really less curves over here. So now how can I see this effect using our new simulator option? So this one is now in advanced option. That's why I was able to go up to 1000 Hertz frequency here in the simulation tab. So if I just bring it closer, I just wanted to see the more clear graphs. So you can see here the graph is really smooth with the advanced simulation mode. Now if I go back to the new options, and if I modify the options to the fast simulation right now, let's say I just move it to fast simulation, and I apply these changes to the project properties and close it. So if I run the simulation at this point here, now you can see here it's really not clear, and there is a lot of choppiness, and it's not good because we are at this 766 Hertz, which is not suitable for running the simulation with a fast simulation phase. So if I go below 200 hertz, you can see here the curve is much more stable and it's much more smoother. This is because theoretically with a fast simulation you can go up to 200 hertz frequency. So if I go below those values, you can see here it's even better values and much smoother curves. You can look at it as well. So this is the latest features that we have added using this new simulator options. So now let's jump into the improved component models, how we can build this improved components model. First, I will start with a simple proportional control valve. So before that, I just close this file. So with this improved simulator options, now you will be able to do the transition behavior of this proportional control valve as well. I'll just quickly open one of the ANSI metric sheet. And I open this library explorer, and I just wanted to show you here first. So I'll just open the library. If I go down and I go to the proportional directional valves and I take a user-defined valve, just drag and drop it. What we have improved in this new proportional directional valve. If you double click on this proportional directional valve over here, if you see here under the data tab, we have a technical characteristics and the technical automation studio characteristics as well. So we have added the new simulation model type. Previously we used to have only the kinematic model, and now we have added a new dynamic model of this proportional valve as well, which allows you to simulate your spool transition behavior as well. So let's say like kinematic and dynamic valve here. So when I put it to kinematic valve, you have access only to the response speed of the spool as well as the spool speed convergence. But when I modify it to dynamic valve, you can see here now you can have access to spool dynamic friction as well as the spool mass. Basically, the spool dynamic friction means the damping coefficient of this proportional directional valve over here. Now I will just create a simple circuit to show you the difference between this kinematic and dynamic simulation over here. So for that, I'll go back and I'll bring a simple double acting cylinder and a pump and a reservoir, and I just go down and I grab a simple pressure relief valve over here, and then I zoom in closer. Just quickly connect it. So I'll copy this component over here. So now I'll just see in this once, and to control this joystick or control this directional control valve, I'll just bring in one of the new joysticks under the set point devices, and I'm going to use variable assignment to control using this solenoid variable. I say in the X direction, I put it input signal, link it. So let's see, like I'll just add some few properties so that we will see more clear dynamic properties of this valve here. So let's say like I have a 90-degree inclination, 1,000 kilograms of external load acting on it. So apply, and I run the simulation up here just to verify if it's working fine. It's good. So just to show you the difference between the dynamic and kinematic model, I'm just going to copy this component over here. And if you see here, the first one is a kinematic model. We will put it to kinematic model, and I will leave the response speed and the spool convergence as it is. And in the second model, I'm just going to put it as a dynamic model, and I'll modify some damping coefficient as well as some of the spool mass, like let's say 2 kilograms. And I close this one. To show the differences between these two valves, I'll open the plotter, and I'll just drag and drop this into the plotter quickly. I apply, and now I'll go to the simulation tab right now. So as you can see here, right now there is no movement in the valve, so basically both lines are intersecting together. So, and then when I just change this joystick, now you can see here bit more clear dynamic behavior. So if I just put it back, you can see here the yellow one is the dynamic valve and the green one is this kinematic model. If I just pass the simulation here, and if I go back a bit behind, if you see here in this one, so previously what we used to do is the kinematic model, which you already had it. With the new model, we are using the dynamic model, which takes into account the response time of this valve according to the flow and the settings on the valve here. So if you see here in this one clearly, the yellow one is the dynamic model and the green one is the kinematic model. Previously, we used to have an approximation in the plotter, so which is basically comes back unsteady, straightforward. Now with the improved model, we have more a dynamic behavior of this valve over here. You can also change some of the properties like a spring stiffness of this valve as well to see the differences. For that, you can just access here, and you can go to the spring stiffness, spring value. You can just change the spring stiffness of, let's say, 2000 Newton per meter, and the other end as also 2000 per meter, Newton per meter. And to compare the effect, I will just change here as well. So let's say like 2000, and the other end as well 2000. So I'll just make this plotter a bit bigger. So if I run the simulation right now, if I just actuate it, you can see here there's more stiffness value. Like you can also compare between the stiffness of the of the valve and see how it behaves, and you can also simulate some of the transition behavior of the valve as well. So this is for the proportional valve. Now let's move to the cylinder and let's see like what behavior it has with the new improved component properties in the cylinder. So for that, I'll just move this one to the right, and so let's say I have like one of the cylinders up here. So I just wanted to simulate the behavior of the cylinder. For that, if I double click on it, now you see here in the improved model of this new cylinder, we have a material density, which allows you to set your mass of the cylinder. So let's say if I just change the density to 8700, you can see here in the mobile mass, the value changes according to your density of the material. And this will be very useful if you wanted to do more component level simulation here. And if I go back in the piston thickness, you can see here you can also adjust the piston thickness to modify the mass. And we have added new extended residual volume and the retracted residual volume as well. So I'll just put back to this one here, and I will just wanted to show the dynamic behavior of the cylinder. For that, I'll just go back to the builder and activate the spring. And I go to the data tab, and I'll just set some parameters. Let's say like if there is 1000 kilograms acting and minus 90 degree inclination of the cylinder. Basically minus 90 means this is like the piston end is going downwards here. So, and I'll set some spring stiffness as well, like 30,000 Newton per meter, and I'll close it. And I add few reservoirs as well. I'll copy this one. So I just open this plotter here, and I will just delete this first two for the proportional valve, and I just drag and drop, and I see the linear position to see the effect of this dynamic effect of the cylinder over here. So if I run the simulation right now, you can clearly see the dynamic effect of this cylinder. So with the improved model, you can now set up your mobile mass to have even more accuracy. And also, like let's say like if you wanted to have some changes in the dynamic friction value. So in the first one, we have a dynamic piston friction as 0.01 decanewton second per centimeter. And I just changed this one to 1 for dynamic piston friction to see the difference between, like, basically this should damp faster than the first cylinder over here. To see the difference, I will drag and drop this one as well. And I say linear position. Run the simulation up here. So now you can see here the second one which we have selected, the yellow one, damps faster than the first one. It's because of this new improved dynamic piston friction value over here. Okay, so now we have seen both hydraulic components which we have improved to accommodate this new feature, new advanced simulation phase. So now let's move on to this electrical motor. So for that, I would like to open one of the projects. It's up here. So this is a simple electrical motor circuit up here if you see. So there is electrical motor. We have improved the behavior of this electrical motor as well to take into account this dynamic simulation behavior. What improvement have we done in the electrical motor? If I double click on the motor here, now you have a new option in this component tab here. So I just drag this one here. If I go back to the motor, and we have a new option in this one here. There is a simulation model. Now you can do modeling by curves or modeling by parameters. If I set to modeling by parameters, you just have to set all these properties over here. But if you model by curves, you will now have access to the characteristic curves of the motor. So let's say torque, power factor, and the current curves that you can add based on the nominal speed versus current. And if I go back to the torque, nominal speed versus torque over here. So you can adjust the curve and you can import the values as well here from the Excel sheet or any other data sheet that you have. And if I just close this one, if I run the simulation here, in this circuit here, this is a variable frequency drive by which we are controlling the speed of the motor as well as the frequency of this motor as well here. So if I do the normal simulation in this one, so you can see here automatically it starts following the curve. So if I start applying some of the resistive torque in this motor, so you can see here automatically it starts following the curve, and for 1428 RPM, you have a resistive torque of 3 Newton per meter. So if I start increasing, if you go beyond certain torque limit here, it will automatically fall down to 0 because physically the motor is restricted and it's stuck. So now, like if you wanted to change the frequency, like if I change the frequency of this motor by adjusting using this a simple HMI component here by using the slider joint here, it automatically adjusts itself the curve, the new curve for this 34.1 Hertz frequency. So you just model for 50 Hertz frequency, and based on your frequency adjustments here, the motor will automatically take the new curve into account. So if I just apply some of the resistive torques to this motor, you can start seeing it starts following the new curve as well here. So basically this is what we have developed in the new Automation Studio with the new advanced features. So you can now use the new simulator options. Once again, I wanted to recap quickly how you can model the simulation, modify the simulation phase. You just have to go to the project properties, and under the project, if you go to the standards, you have two tabs, edition and the simulation tab. You can set the simulation phase over here, normal, advanced, or fast simulation phase. And we have seen the improved component models as well. The first one is the proportional directional control valve with the improved dynamic behavior model, that kinematic and dynamic model. And in the cylinder, we have also seen some of the mobile density in the mass, and also added some of the external residual volume and other parameters like dynamic piston friction and things like that. So that's all.